Differentials can be used to do approximate calculations. And the idea of using differentials for approximate calculations is this. So I want to repeat again the linear approximation formula. So linear approximation formula is this. F of x is approximately equal f of a plus f prime of a times x minus a. And now I want to subtract f of a from both sides. So f of x minus f of a is approximately equal to f prime of a times x minus a. And now here is how we can interpret this formula. Let's say that x is a certain physical value that was measured, and it was measured approximately, not precisely. So let's say that a is approximate measure or approximate measurement, and to x was precise measurement. And since our tools to measure are not perfect, so we do know approximate measurement that the tool shows, but we don't know the precise measurement. We do know though that they are close to each other because our measuring tool is actually good, or supposed to be good. Now, if this is approximate measurement, then let's say that we use the function f of a to calculate something based on that measurement. For example, we measure velocity of a moving object and then use a formula from physics in order to calculate the energy of that moving object. So f of a will be approximate calculation of that energy or whatever we are calculating. So it's approximate calculation, and f of x will be precise calculation of that energy or whatever that value is. And the difference between precise calculation and approximate calculation is actually error of calculation. Error of calculation. So here's what we have. X minus a, which is precise measurement minus approximate measurement, is actually error in measurement. So some quantity can be measured only approximately, only up to certain error. And then the other quantity based on that can be calculated also approximately, also up to certain error. And because the initial quantity was measured with an error, so the other quantity is also calculated with an error. But this error can be calculated more or less precisely. So here's an example. Here's an example. Radius of a circle is measured as approximately 10 meters. But this measurement is approximated, not precise. All we know is that error of measurement is approximately 1 centimeter. So with error of measurement approximately 1 centimeter. It's actually plus or minus 1 centimeter, or plus or minus 0.01 meter. In fact, if you think of it, it's a very good measure, because actually it's 0.1%. It's 1/1000th of the value. So it's a pretty good measurement. However, it's still approximate, it's not precise. So what it actually means, it means that precise measure of that circle, it doesn't have to be exactly 10 meters, but it's between 10 meters minus 0.01 and 10 meters plus 0.1. So let me put it in brackets. So the precise radius is between 10 minus 0.01, which is 9.99, and 10.01 meters. So the actual measurement of that circle is between this and this, but we have measured it as 10 meters. Here is the question. We are calculating the area of the circle. The area of the circle is then calculated as, of course, pi r squared, but since pi is 3.14 approximately, and radius was calculated as 10 meters, so it will be 10 times 10 squared, which is 3.14 times 100, which is approximately 314 meters squared. Again, since the radius itself was measured only approximately, so the area that we have calculated is also approximate. And here's the question. Now, this is approximate, it's not precise. And here's the question. What is the error of this approximation for the area? Like, we know the boundaries for this radius. So what are the boundaries for the area? Which means how good or how bad is this approximation? How good is this approximation? And here is the idea. The idea is that the approximation of area can be denoted by delta x, can be denoted by delta y, because area is y. Let me put it like this. So area is y, and approximation of or error in calculating the area is delta y. And we know that delta y is approximately equal to dy, the differential, which is f prime of a times dx. Once again, here is another way to interpret this. We start with f of x approximately equals f of a plus f prime of a times x minus a. And then we subtract f of a from both sides, so it's f of x minus f of a is approximately equals to f prime of a times x minus a. Now here's what we have. X minus a is error in measurement. The exact value minus the approximate value is error in measurement. And we know this error, it's 0.01 meter. This is the error in calculating the area. Error in calculating the area that we want to find. It's unknown. This is what the problem is asking us to find. And to find, so it's equal this time. So all we need to calculate now is f prime of a. So what is f prime of a? So f prime of a is just Well, in order to calculate f prime of a, first of all, what is f of x here? F of x is the formula. F of x is how area depends on the radius. So f of x is how area depends on radius. So now radius is x. So f of x is just pi times x squared, because x plays the role of radius now. And in order to figure out this, we need to do derivatives. So f prime of x is pi times 2x. And f prime of a, therefore, is f prime of a. And a is known. A is the approximate approximate measurement of the radius, which is 10 meters. So f prime of a is pi times 2a. And a is 10 meters. So what we got is pi times 2 times 10 meters, which happens to be, well, since pi is 3.14 times 2 times 10, 3.14 times 2 is 6.18, and times 10 is 62.8. So it's a 62.8. 62.8. So that's f prime of a. So this is what we plug in here, 62. So I can erase this question mark now. So this is just 62.8. And now that's it. I mean, all we need to do is just multiply together 62.8 times 0.0 times 0.01. So we get that error in calculating the area, which is denoted by delta y. By the way, delta y is approximately equal to 62.8 times 0.01, which equals 0.628. 0.628. So this is the approximate, what are the units? The units, of course, meters squared, because we're talking about area. So this is the approximate, this is the error in calculating the area. Now here's what we got actually. The radius of that circle was measured with error of just 1 centimeter, 1/10 of a meter. But the area of the circle was calculated with error of almost full meter squared, like 0.62 meters squared, which looks like pretty large. Now, actually, it's not that large. I mean, when you look at the absolute value of the number, it does look large, like 1 centimeter error in measuring the radius makes you almost full square meter of error in calculating the area. It looks like very big error. Is it very big? Actually, no, it's not very big. Let us calculate the relative error. So this is called absolute error. Absolute error. And this absolute error, again, it's almost a full square meter. If you think of it, it's a huge error. But in practice, we often calculate, instead of absolute error, we calculate relative errors. So let's do that. Relative error. Actually, relative error is the ratio. Like for the radius, it would be delta x over x, or for the area, it will be delta y over y. So let's calculate both relative errors and compare them. So for radius, relative error is well, the absolute error for radius was 0.01, which is 1 centimeter, divided by the total value of the radius, that was 10 meters. So 0.01 divided by 10 is 0.001, which is basically 1/10 of a percent. It's 1/1000 of a percent. That's for radius. Now let's calculate the same relative error for the area. For area, relative error is, well, again, it's a ratio. Absolute error divided by the value. Absolute error is here, so it's a 0.628 divided by the value of the area. And what is value of the area? Well, the value of the area, I think I have calculated it somewhere, but if not, I will calculate it now. So area is pi r squared, and since pi equals 3.14 and r is 10, so it's r times 100. So it is, so now let's calculate the relative error for the area. For area, relative error it will be delta y over y. In this case, delta y for area is 0.628, and the value of the area is here, it's 314. So when you divide over, you get 0.002, which is actually 0.2%. 0.2%. So what it means that 1/10 of a percent error for radius brings to 2/10 of a percent error for the area. So even though absolute error for area looks like a large number, almost a full square meter, but when you divide it over and get relative error, so it's pretty small. In fact, it's equal to it equals twice relative error of the radius. So the relative error for